At this point, we've successfully joined the American Community Survey data to our block group geography. In this case, we've joined 4 columns: the population 2015 5-year estimates for Amesbury by block group. Again, remembering that these are estimates that span 2011 to 2015. The margin of error for those estimates, the 2013 5-year estimates, which extend from 2009 to 2013, and their margins of error. So now we can analyze this data, and the estimates are clear enough. These are estimates of the total population for each block group. But the question is, what are the margins of error and how do you handle them? Well, the margins of error are essentially numbers that tell you the precision of the estimate at the 90% confidence level, which is to say that we can have 90% confidence that the real population number for each block group falls within a range of this value. And the range is described by that margin of error. We can visualize that by computing that range, simply adding and subtracting those values from the estimate. So here we've created a column for the upper value of the range, which we could call a confidence interval. And we added the margin of error to the estimate, and we have the lower bound of that confidence interval by subtracting the margin of error from the estimate. And so we'd say this is again, the idea being here that the true population value for each block group is with 90% probability lies somewhere between those two numbers. And so you can see that in some cases it's a considerable range, but that's important because that tells you then that the trust that you can have in the number can only go so far, since all of the ACS data is in fact an estimate based upon a sample. They did not actually survey the entire population. You could ask for a higher level of confidence, 95% or 99% even, but what's going to happen is that you're going to keep increasing the range of values. And nevertheless, it's important to understand that because that's the trust that you can have in the numbers that you're working with. The margin of error is particularly useful because it allows us to compute a variety of other sampling error measures. And the one that we're actually most interested in is this standard error, because the standard error will allow us to compute the other measures that we want to look more closely at. So the standard error can be computed from the margin of error by simply dividing the margin of error by 1.645, which is the value that was used to create the margin of error in the first place. 1.645 is a critical value, which includes a particular range around the statistic in order to be estimated. So the standard error that we've computed, dividing the margin of error by 1.645, tells us the variability of the estimate. It's essentially analogous to the standard deviation around the statistic. But because we're working with the sample, we don't have a standard deviation. We have instead a standard error. But essentially, they're kind of the same concept. In a way, if you have a normal distribution of values, you could say that you could have 68% confidence that the true value lies somewhere within the upper or lower range described by these values, which is a low threshold of confidence, which is why we don't use it. It's more common to use values of 90%, 95, and 99%. In any case, this number is actually kind of an interim number. It's going to allow us to get at other statistics they were interested in. In particular, what we want to do is calculate the coefficient of variation, And that's just another measure of variability, but the nice thing about that value is it allows us to compare between the block groups in order to see where there is more or less relative variation in the or variability in the statistics. So the coefficient of variation is computed by dividing the standard error by the estimate and then multiplying by 100. These values represent percentages, so we can say the percentage of variability around our statistic. So if we wanted to map these, we could look at how the population estimates vary around that. We can see that in some parts of the community there is more variability in the statistic compared to other parts where it's a little more stable, and we can directly compare these values because they are all percentages and so they're relative to the values, whereas the standard error are in a sense absolute values which aren't directly comparable between each other because they depend on the magnitude of the estimates. Okay, so the coefficient of variation and standard error we've computed from using the margin of error. Now the next thing we want to do is we want to be able to determine whether there has been a statistically significant change between two estimates. In particular, we want to look at the last time period, which was the 2013 5-year period, and compare it against the 2015 5-year period. And we need to do this. We need to use a statistical test of significance to do that, to see whether there's been a significant change. So you can tell by looking directly at the population 2015 and the 2013 values that there are differences in the values. But when you take into consideration the margins of error, it's not always clear if those differences are real and they're not simply due to the chance, the variation in the value. So first up, let's just simply compute the differences to get a sense of that. So when we look at the differences between the estimates, we can see in some places there was an apparent decline between 2013 and 15, and in some places a growth. But again, the question is, are those differences real given the margins of error, or rather the variability of those statistics? And the way that we compute that is to use a test of significant difference. The test for significance is carried out by making several computations using the estimates and their standard errors. Algebraically, the significance test can be expressed with this particular equation. And the equation describes, essentially we're taking the difference of the estimates and dividing it by the summed squares of the standard errors. But because we're making a comparison between two multi-year estimates that have overlapping sample years, you see that there's a significant overlap of a few years. We need to account for that overlap by making an adjustment to the formula. In this case, what we're going to do is we're going to insert the square root of 1 minus c and multiply it times the square root of the sum of the squares of the standard errors, and c is the ratio of the overlapping years. So in this case, the periods 2009 to 2013 and 2011-2015 overlap for 3 out of the 5 years. So c essentially is 3 divided by 5, or 0.6. So in order to compute the test of significant difference, I need several values. I need to have the difference between the two estimates of interest, the two time periods I'm comparing, and I need to have the standard errors for both time periods. We'd previously computed the standard error for the POP 2015 estimates, and now I went ahead and did the same thing for the POP 2013 estimates. So now we have all the values that we need for this. And so we're going to first square the standard errors for each estimate. So to square the standard errors, we are going to raise them to the power of 2, and using VB script, that means we use the hat symbol, which is above the 6. Next, we need to sum the squared standard errors. Finally, we need to, well, not finally, we're almost there, calculate the square root of the sum squared standard errors. We need to also derive the square root of 1 minus c, because we're going to need to multiply it by this value. We can actually complete this part of the calculation in one field. So we're going to take that square root of 1 minus c, 0.6, and multiply that by the square root of the sum of the standard errors. Finally, we're going to divide the difference between the two estimates, the xdiff, by that 1c. And what we have now are our critical values of interest. So this is what we were trying to get to. So what we're interested in when we look at these numbers is the absolute value of them, and in particular we're interested in finding out whether any of these absolute values, whether the absolute value of any of these values exceeds the critical thresholds of interest. So if we wanted to have a 90% confidence that there's a significant difference, any value that any of the numbers here that has an absolute value that's greater than 1.645 would satisfy that criteria. If we wanted to work at the 95% confidence level, it would be 1.96, and if we wanted to be 99% confident, then it would have to be greater than 2.576. And right off the bat, I can see that we have at least one value that exceeds the 95% confidence level, which is typically our standard measure in the scientific literature, at least, for a significant difference. But if we wanted to lower the threshold to 1.645, well, that's pretty much it right there. So there we have the one block group that shows a statistically significant difference at the 95% confidence level in terms of the population estimates between the 2015 5-year estimates and the 2013 5-year estimates.